Hello, hello. 1 second.
Good afternoon, Professor.
Good afternoon, Laitule. Thank you. Good afternoon. Good afternoon, Katie. Okay, sorry. Yeah, Katie. Hello, Tiggy. Okay, I'm going to say more hellos in 1 second. I'm just getting the board coming in here. Hold on. Okay, and the one. Okay. And good afternoon, Yatron and Angela, thank you for having avatars. And yes, good afternoon, Caitlin. Hello. Oh, I missed Caitlin. I'm sorry. Good afternoon, Caitlin. Hello, Tiggy. Good afternoon, Montserrat. Good afternoon, Michael. Good afternoon, Mohammed. Good afternoon, Yatron. And thank you for, I like the avatar or the picture. Good afternoon, Sadie. Oh, good afternoon, Sadie. Okay, second. That's awesome. Okay, what the screen, the board, the. Okay, who else do we have? Okay. Long time no see. Thank you everybody for handle. Oh, and hello, Mira. That's a real Mira. Hello. That's awesome. That's a huge amount of points. That's terrific. Okay, I appreciate it. I will stop calling attention to it, maybe. No, that's terrific. It's good to see you all. It's been a long time. Thank you. Many of you, well, like I think all of you responded to the communication about no class. I appreciate that. Oh, I know it didn't go through to, oh, and hello, Sadie's picture also. Thank you. And more people coming. And good afternoon, Josh. Good afternoon. Okay, more people coming. Sorry. All right, we'll get this party started. Okay. Okay. And who did I just, that was Josh. Yes. Hello, Josh. And welcome, Carla, and welcome, Madonna. And good afternoon, Madonna. And good afternoon, Carla. Thank you for having a picture or an avatar. I appreciate, well, a picture. I appreciate it. It's awesome. Okay. So yes, I mean, good afternoon. I just said that, right? Okay, yes. Good afternoon, Carla. Awesome. Okay, so good afternoon, and good afternoon, Mohammed and Amalei. I'd say it wrong every time. I'm sorry. It's like the movie Amelie. What's my problem? Amelie. Good afternoon, and correct me if I'm still wrong. And Mohammed, I didn't say hello to, and I think that's everybody else. And Jamie's coming now. Okay. So yes. I know that's one of the reasons I do my whole complicated thing whenever I can't be there to teach a class is, partly it's to incentivize everybody to make sure to check for communication, because they definitely do not ever want to have someone waiting in a physical classroom or a electronic waiting room for a class that doesn't exist. I mean, so I apologize if that happened to a person or two last time. I feel bad about that. But for most of you guys, so that's why you get points just for having the communication. But then also many of you then followed up and watched the video and responded to the video. Hello, Alirat, good to see you. And hello, Takarub, good to see you. Good to see you in 3 dimensions, or well, in animated form. Thank you, Takara, for showing video. So good to see you all. And yes, thank you for those of you who watched the video and tried to get something out of it, and did get something out of it, and then wrote to me what you got out of it and what you're still struggling with. That's all very helpful. It's going to help today's class more. Of course, I know that a Zoom class is not quite the same as a physical class, and a video is not quite the same as a Zoom class. I understand all that. So we're getting whatever we can get out of whatever we can. But today's class is going to be that much better as a result of the feedback and responses that you guys gave me about the video. If you happen to be one of the people that knows what I'm talking about, that knows there was a video posted for last week and still hasn't watched it or like responded to it in order to get the points, like with almost everything else in this class, it is not too late. It would be highly recommended to still watch that video. It will, and you'll still get the points and all of that. Like, it's, I think, easier on everybody if you do things in sequence and if you stay caught up, but catching up after the fact is certainly better than missing out completely. All right. So I think that, so anyway, today, and hello, Roland. Welcome, welcome. Today, oh, and Alex, I never said hello to Alex, I don't think. I'm sorry. Hello, Alex. Okay. Today, I mean, I have an agenda as always, and I will get to some of it as always, but I do, because I didn't see you, I know what work we need to talk about, or I believe I know what work we need to talk about, and what problems we need to go over and so forth. But before we do that, since we haven't seen each other in a while, can I get a little bit of updating and input from you as to what you got out of Tuesday's lab? This, I mean, I know what you did. I mean, I did speak with Professor Moses before and a little bit afterwards, but actually only a little bit. And I know Dr. Prony was in the room also. So I actually got a little bit of input from her. So I'm not blind, but or it's not. I'm not totally in the dark, but I'd love to hear from you what you think you got out of or didn't get out of the lab on Tuesday. And also hello, Jamie, if I didn't say hello, Jamie. So anybody just anything, like, what do you think the takeaway was, or what was difficult, or what do you still have a question about, or anything just from any of you, either in the chat or in the private chat or with your voice, just like give me a brief update on what either got clarified or needs to be clarified from 2 days ago.
I could say something.
Great. Thank you. Saving the ship. Thank you. Yes, please do. Okay.
So in lab, what was it? Oh, we did the GIFs. Yeah, so starting at different points in the graph, we created the curve, and we did a GIF from each, point, as time went on, we changed the point and you just saw it through the GIF. And then the last thing was we put all of them together on one graph, which was I think that was the best part. Put everything together, and then it allowed us to like see everything as like a full picture type situation.
Cool. Thank you. Okay, that is very helpful. Okay. A couple of questions. Okay, that's great. And I'm glad you liked the last part. The last part is definitely a hit or miss, I suppose. That's good. So with the GIFs, so I'm going to ask follow-up questions to what Josh just said. Josh is welcome to answer the follow-up questions, but it doesn't have to be Josh. It could be anybody. Each frame that you made to make the whole movie, to make the GIF, they were all points on a graph, right? Everybody who did anything, you were ultimately animating actual graphs. Is that correct?
Yeah.
Okay. See,
I'm understanding you correctly. Yeah. It was points on a graph already. We just animated it.
Right. Okay. You are understanding me correctly. No, it's interesting because that's actually been a accidental evolution in the lab over time. That's not the way the lab always was. That's why I'm just clarifying. But yes, you're understanding my question correctly. Okay, good. Oh, wait, I'm looking in the chat. Professor Moses also explaining. Okay. Oh, I'm looking. Thank you for all of this in the chat. This is great. I'm really glad that Josh got us kicked us off here, but I really appreciate that everybody else is also taking up the mantle. So I'm looking in the chat right now. Each photo was 1 point on the graph. Okay. Whoa. Oh, cool. Oh, all right. So the last part was cool. Okay, like a DNA double helix structure. Cool. Right, because it's like 3-dimensional. All right, awesome. I'm just looking more and more. Then there's also some things, forgive me, there's also some things in the direct chat, so I'm just reading them to myself. Wow. Okay. Good. All right. I'm reading everything in the chat. Obviously, you can all, it sounds like the last part was the coolest. I'm psyched for that. I'm psyched that it was cool. Okay, I'm also going to read, I'm not going to read I like how, like, Caitlin is saying that you, part of the takeaway of the lab was relating waves to the unit circle. That is cool. And then there's another thing in direct chat. I'm not going to read the person's name, obviously. But another thing in the direct chat says, it became clear to me that the wave-like graphs that we got in previous labs were showing the unit circle as if taking each 1/4 of the circle and moving them to get the wave-like graph. That is interesting. I do know what the person means. That is interesting. I'm very glad. This is cool. In a way, this is like my ideal. Like a lot of you are saying that you like the last part because it was cool and good. I'm glad it was cool. I mean, it's cool to me, certainly. And I'm glad if it was cool. But you also seem to be tacitly recognizing that the last part is a bit of a stretch. I mean, maybe you had, well, I guess I could ask this. You might have had a discussion with Professor Moses in the room about the extent to which the last part is or is not actually a wave. Like, I guess I'll just assert, I mean, if I understand the way the lab is now, if I correctly understand the way the lab now is, which is a little bit different from the way it once was, you sort of are creating a wave, you're simulating a wave once you animate these GIFs, once you turn it into an animation. But then when you go that extra step right at the end, which I think is an extra step, then you're almost like, the reason it's like three-dimensional and like a double helix and like cool. Oh, cool. Someone's, cool. People are sending me pictures in the direct chat. Okay. I like the picture that's in the direct chat. I'm going to ask the direct chat person. I may or may not want to actually copy this picture and put it into the chat for everybody to see without anybody's name. But can I just ask, direct chat person, the picture that you're showing me, is that the very last, is that a screenshot of the very last bit of the whole lab, or is that before the last bit? It's after. Okay. Let me see if I can easily copy this without using anybody's name. I'm going to, just so everybody can know what I'm talking about. I think I can. Yeah, it looks like, okay. So hopefully, so direct chat person, do I have permission to, I'm going to, oh, wait. Oh, well, here comes, okay. Oh, wow. No, that's cool. Oh, and I have permission. Okay, great. Thank you for the permission that you knew I was about to ask for. Okay. So this is cool what Ye-chan just put in for everybody. And it's cool that it's sort of like, it's like a 90-degree rotation version of what I'm now sharing from, oh God. Oh, wait, did I? Wait, 1 second. Hold on. All right, I might have just. Okay, I think. Okay, so now you have two pictures in the chat, which of course you've already seen. It's me that you're showing them to now in a way, but okay, this is all very cool. This is very cool. I'm glad it was cool. It was meant to be cool. I mean, it was meant, it was meant to be sort of fun compared to some things. But I'm also glad that people in the chat and in the discussion are pointing out that we're sort of trying to connect this to or from the unit circle. And that's where I want to go back, when I start lecturing in a couple of minutes. One piece of feedback that I've gotten from people, like about the movies, the videos that you watched last week, and about the general issue, to a number of people, at least as of last Thursday, it was still a bit of a confusing issue why radians and radians per second or why phi, that extra Greek letter, the Greek letter that's right at the end of the first equation on the board right now, that thing which is measured in radians, why all these radians and angles, much less cosines, are coming into a discussion about something that's going back and forth in a straight line. Like a number of you in different ways are raising that question, or in fact, some of you are even implying in your feedback to last week's video that you kind of do get, like a larger sense how radians might be coming into play here with something that's going back and forth in a straight line. But that doesn't, but you're still admitting, some of you, like, even though I sort of get why they're coming into play, I don't really get directly how to exactly use radians to express anything that's going on with something that's going back and forth. And I think that's a very, very fair and reasonable and frankly common concern for people to have at this stage. It is confusing why something going back and forth in a straight line is suddenly talking about angles and radians and all that. So I want to try to flesh that out more today, or flesh out more how to specifically make that connection. So yes, 2 days ago, the lab was meant to provide more meat on the bones to that issue. Like, it's supposed to give you more of a visual sense or an intuitive sense of how the unit circle is turning into oscillatory behavior. So that's good. If yesterday's lab, 2 days ago's lab helped you at all start seeing where circles and cosines and radians have anything to do with something going back and forth, that's really good. I will also say, though, that it probably doesn't fully seal the deal for everybody, because in part, what I now want to turn back to in a minute, in part, what Tuesday's lab is meant to do, but it does it in a very risky way. Tuesday's lab is meant to show you a big, big connection between simple harmonic oscillation, which is what we've been talking about in lecture. It's meant to show you a big connection between oscillation and waves. Like, that's the big thing that you did on Tuesdays. You used a bunch of oscillations and put them together to make a wave. That's great. And if it was cool, all the better. But I want to just say right now, as a warning sign, there's a huge connection between oscillation and waves, yes, and that's what you're seeing. And there's a huge connection between oscillation and the unit circle and cosines and radians and all of that, yes. So if you're seeing the connections, that's great. But there's a big risk that we're running here, a big danger that often happens with people, is that they start seeing the connections so deeply or so visually that people start confusing the issues and lumping them together into one. Bottom line, what I want to say right now, and then I'm going to start lecturing, but of course, interrupt me at any time with any questions at all. But bottom line is, an oscillation is not the same thing as a wave. What you are creating Tuesday were waves. Waves require oscillations. So all waves involve a lot of harmonic oscillations, but not all oscillations are waves. Okay, that is a really important distinction to make and can get very lost in translation. And in effect, I guess what I'm going to say right now is what's on the board right now. And of course, I'm going to start talking in a second. But please, again, because I run such a risk of just talking for 2.5 hours in this class, please stop me at any time to tell me to go back or to tell me to go forward or whatever. Or just stop me with something that it might be on the side, because maybe what you think is on the side is actually more important than what I think is in front right now, honestly. But I'm going to emphasize that more again, because I'm always scared of a 2.5 hour class. Like, it's so risky for everybody to sit here for 2.5 hours on Zoom. So let me also remind you, if there's the slightest issue in your mind at all, and you think it might be important to you, but you are not sure whether it's important to me or to the rest of the group, then that's what direct chat is for. Take the risk. I promise you, at worst, I'll say, I can't deal with that right now. Please text me, but I won't shame you. Really, direct chat is the one advantage we all have in a Zoom class. So, because I'm going to start talking. Once I start talking, it's, it's so, so here, okay. So someone just did. Okay. So pardon me for a second. I'm gonna, hold on. Oh, okay. So hold on. So there's a couple of questions in direct chat. I do want to deal with. Hold on. I'm just looking. Okay. Wow. Great. Oh, okay. So I'm going to say right now, I'm not going to mention any names, but but someone in the direct chat is saying something to the effect that Professor Moses showed that if you open up the unit circle, you get a full cycle. Is that correct? I was a little confused by that. Very legitimate question. Okay. That's something I want to deal with today. I mean, my short answer to that is, oh yes, if you walk around the whole unit circle, once, that is the mathematical version of physically experiencing one full cycle. I mean, yes, the big thing that I care about, that I think Professor Moses was trying to get at with that, or was getting at with that, is all of these cosine functions, all of this math, what it's really doing is taking the mathematics that we already know for a full circle, and it's grafting that mathematics onto what we are now physically concerned with in a full cycle, which absolutely the case. And yes, so I mean, my big answer is yes. Like, the transposition that we want to make in our minds in order to make sense out of all of this is whatever we believe that we know mathematically about walking around a full circle, we are using those mathematics to analyze physically experiencing a full cycle. And in physics, in the physics that we're doing right now, when we think of a full cycle, what we mean is there and back. Like when a mass on a spring goes all the way from positive amplitude to negative amplitude and then back to positive amplitude, a there back trip, a round trip, doesn't need to be, I mean, the word round trip says it all. When we say in English something made a round trip, we mean it went somewhere and it came back. Note that when we say round trip in English and in physics, when we say the mass made a round trip from front to back and back to front again, we call that a round trip, but there's no roundness to it at all, right? It's doing it all in a straight line. There isn't a circle to be seen. But because it's a full cycle, because it's a repetition, because it goes there and goes back, we start borrowing, even in English, we start borrowing the language of circles, and we call that a round trip, even though it's not round. It's round in the sense that you go around, you come back. So absolutely, I'm going to agree in English that our idea is we already understand a lot about the math of circles. We particularly understand that certain things are true of circles no matter how big they are. Certain things are true of circles no matter how big they are. We really like that about circles. Therefore, we borrow certain things that we already understand about circles to apply them to cycles, and we do that because we don't want to have to care or know how big a cycle is in order for all this math to be true. So my short answer is yes, absolutely. Now I'm going to do it more my way. I'm going to get more specific about that my way. But yes, direct chat person who asked. So I'll be more expensive. But yes, if you open up the unit circle, you get a full cycle. All right, maybe I want to dive into that right now. Hold on. That's a long way of saying, please do stop me if you have any doubt in your mind whether it's appropriate for the class, please assume it's appropriate enough to send me a direct chat. And at worst, I'll say, okay, not now, But really, the more you guys do say and type things, the more invested we're all going to be. Okay. That said, I think that's it for the. I'm just looking in the chat again. Okay, I think that's everything in the chat. Oh, so one last summary comment of where we're going with this. The top equation on the board right now. Well, yeah, okay, actually. The top equation on the board right now is one simple harmonic oscillator. What is a oscillator? The bottom equation is a collection of what I'm now going to call SHOs. Like SHO now stands for simple harmonic oscillator. Okay. So the top equation is a oscillator. The bottom equation is a whole collection of oscillators staggered in phase by a constant amount. Now I may have to develop. I'm just in theory. I'm just reminding you right now. In theory, I'm reviewing a statement that in theory you already know from the lab and from the videos. But from the feedback and from these questions, I'm not really assuming that it's 100% firm in your mind. But the top equation, like the two equations, are very similar, but they're just different enough in that last term that really what the two equations represent is the first one is just a oscillator, which is what we've been talking about for weeks. But the second equation is what happens if you take a bunch of oscillators, put them next to each other, and a bunch of identical oscillators, a bunch of oscillators that are the same in all respects, same mass on each one, same spring stiffness on each one, same amplitude on each one. You take a bunch of oscillators that are all, say, aligned vertically, but you arrange them horizontally. Okay, I'm saying this quickly because in theory you've already seen this, but you take a whole bunch of oscillators, and a whole bunch of vertical oscillators, and you arrange them horizontally, like you put a bunch of masses on springs, all laid out on a long x-axis, and you distribute them evenly along the x-axis, so that the 0th oscillator is at the edge of a meter stick, and the first oscillator is at the 1 centimeter mark, and the second oscillator is at the 2 centimeter mark, et cetera, et cetera, et cetera. And you arrange them all so they're all identical in all respects, except that you start all the oscillators at different phases, at different points in their cycle, right? So you start the first one maybe at amplitude position, then you start the next one maybe at the equilibrium position, and you start the next, like they all start at the same time, but they all start at different points in their cycle. And if you ensure that each one of them is advanced in phase by a constant amount. So again, like in other words, the first one has no phase head start at all. Or the 0th one has no phase head start at all. The first one has a phase head start of like pi over 2 radians, for example, which would be like a quarter of a cycle, for example. And then, so the first one is ahead by a quarter of a cycle. And the second one is ahead of that by a quarter of a cycle. So that in fact, it's ahead of the very 0th one by a half cycle, and the next one is ahead by 3/4 of a cycle, and the next one is ahead by 4/4 of a cycle, right? If you distribute a whole bunch of identical oscillators, if you distribute them all uniformly along an x-axis and distribute their phases all uniformly, then what you have then is the second equation on this board. What you have then is what I would call a collection of phase staggered oscillators. But bottom line, big punchline of what in principle you saw in action in the lab 2 days ago, and big punchline of what in principle was being explained in the video last week. This another word, there's a 4-letter word to describe what this phenomenon ends up being. I'm going to ask you in a second. Like once you take, like once you take a whole bunch of oscillators and you put them together in a collection that's very, very deliberately arranged in the manner that I just described, you take a whole bunch of objects, each of which is moving in a certain pattern in time, but then you arrange all those objects in this kind of pattern throughout space. This collection of phase staggered oscillators all creates one big type of motion phenomenon that can be described in 4 letters, the first of which is the letter W. What am I talking about? Like, yes, and we're going to get, yes, all this. So the answer to the direct chat person is yes, we're going to get, this is going to get us back to going over the homework. Absolutely. But what's the 4-letter word that I'm looking for that begins with W that is ultimately what this collection of phase staggered oscillators describes? Thank you. Someone just said it in the direct chat. That's awesome. And one person did, maybe. And since it's direct, oh, good thought. Wait a sec. Okay, I just got 3 responses in the direct chat. Well, I got 2 responses in the direct chat and 1 in public. And I totally appreciate all the responses. The second response I got in direct chat was very, very clever and was a 4-letter word that begins with W and totally does apply to physics. It was a very clever response, and that person should apply for, submit for extra points in the, in the game terms. But in fact, the word I'm looking for is the one that is in the public chat right now. I just want to make it absolutely clear, and then we're going to go back to the homework. Was it homework 2 or homework 3? I think we have gone. Oh, no, I guess it was homework 2. Yeah. We are going to go back to the homework, yes. But I want to make clear, if there's no other takeaway from the last set of videos and from Tuesday's lab, is this second equation describes wave motion. I can't emphasize this enough, that wave motion requires simple harmonic oscillation, but they're not the same thing. One oscillator is one oscillator. When you make a graph of its motion, its graph does look like a wiggle, but that wiggle by itself is not a wave. That is a wiggle. That is something that's going up, that looks on piece of paper like something that's going up and down in space, but on paper, it ain't going up and down in time. Or put another way, if you read the actual graph of an oscillator, you have time on one axis, you have position on the other axis, you are graphing something that's going back and forth in time. That is not a wave. It's not a wave until you take a whole bunch of these things and you spread them out in space and you arrange them very deliberately. I'm saying in the end of the day, a collection of properly phase staggered oscillators is what makes a wave, and vice versa. A wave requires a collection of phase staggered oscillators. We are studying oscillation really intensely so that we can understand waves, okay? And finally, if in order for a bunch of oscillators to make a wave, it's not good enough just to have a collection of oscillators. You can't have a bunch of masses all next to each other in a line, all going up and down together in the same way. That would just be one huge oscillator. For oscillators to create waves, the oscillators have to be staggered in phase, which is why we have to understand not just the omega t term, but the phi term, the phase term in the math of one oscillator in order even to go to that next step and make a wave out of it. So yes, in a moment, I promise, I am going to go back to the homeworks and start just like walking through the homeworks, like as is my job, right? I'm going to start walking through the homeworks, but I want you to bear in mind when I'm walking through the homeworks to sort of catch us up to where we are now. The homeworks that you had until this point, the homeworks that you had until like the video assignment and until last lab, they were all about individual oscillation. They're all about the cosines and the radians and all of that, which I'll break down further. They're all about individual oscillation. One individual oscillator is a particle moving back and forth according to the classical laws of mechanics in space. Once you put a bunch of particles together in a very specific fashion, this second equation, then and only then do you have ripples propagating through space in the manner of what we call a wave, and in a manner that is ultimately not particular or material in any way. Wave motion is not particle motion. It's not material motion. It's immaterial motion. And in order for it to happen, we need a collection of particular oscillators. So I just want to get that straight. All right, but I know at least one person wants me to go to the homework, and I think that's a good idea. And that's what I'll do. So let me go. So let me turn to the. But stop me again at any time with any questions. But let me. I'll turn to the homework right now. Bear with me. Let me just get it. Yeah. Okay. I'm just pulling it up. Right. I feel. Yeah. Okay. Okay. So stop me if I'm wrong, but I don't think we've gone. I know we've had homework 2 and 3 assigned at this point. And I think we have not gone over even homework 2. I mean, I think that's what someone's asking me in the chat. So stop me if I'm wrong, but I'm going to start with homework 2. And some places I'm going to go over it faster and some places slower. Um, um, uh, So tell me if I'm wrong in the chat. Tell me if we've already gone homework 2 or any part of it, and I will definitely take that seriously. Hold on, I know someone's here too. But I also want to say, and again, as always, because I know we spotty, like we missed class, like we blah blah blah. No matter where you are with the homework, you can still, whether you've gotten points and no feedback, or whether you've gotten feedback, or whether you haven't turned it in, no matter what, I'm going to go over stuff now. You can still turn it in. But as a couple of people in class have been asking me, some of these things in the homework are quick exercises. They're sort of hard to really do the 5-step method for. I recognize that, and I will try to be more take that into account more, be more aware of that when we have our exam. I think these first exercises on homework 2, it's hard to do the 5-step method in a way. I mean, honestly, arguably, I bet you could do the 5-step method for the first one and then refer to that for all the rest and not repeat yourself. But I understand, and that's okay. What I'm going to do also right now, just so that we're all clear, I'm going to switch screens. I mean, I'm asking you all to take out homework 2 in front of you. Whether you've done it or not, take out the sheet and put it in front of you. But what I am also going to do now, just in case, so that we're all on the same page, I'm going to switch the screen share briefly, just so you can see what I'm looking at. And if you need to take a screenshot of it really quickly so that we're all on the same page, please do. So this is what I'm looking at right now. Please either have this in front of you or take a screenshot. And I'm going to ask you, once you're good, once you either have it in front of you, or at least you know what I'm talking about, or you've taken a screenshot, can you just put up your electronic hand? Or some kind of hand? Like I'm going to, put up your electronic hand if either you have this sheet in front of you, or you're able to just take a quick, I want to make, okay, thank you. All right, thank you. All right, thank you, Alex. Thank you, Montserrat. Thank you, Sadie. Thank you, Josh, sort of. Yeah, okay, thank you, Josh. Okay, thank you, Amelie, whose name I keep mispronouncing, and please tell me how to pronounce it correctly in the chat. Thank you, Michael. Thank you, Mira. Okay, awesome. Okay, because is it Amelie or Amelie? I keep saying it wrong. Sorry. Okay, that's good enough for me. Okay, and it's in the chat. All good. Okay, and thank you, Sebastian. Okay, all right. So now that you've done that, thank you all for raising your hand. So now that we all got that, I'm going back. So I'm going to now start using my screen. Okay. Okay. I'm going to all right. So for the first, I think I'm gonna do a 5-step method for the first, just to show you that. So the first thing, so first we have to do a diagram of fact pattern. So what's my step one of the 5-step method, is always diagram fact pattern. And again, one thing that is hard to get used to but important is if the problem doesn't provide its own diagram, that is all the more reason that you should provide a diagram. So the diagram here would be the unit circle, as Professor Moses explained. So the unit circle, as you know, so again, I feel like it's pretty apparent to me that you really did do this with Professor Moses. So I'm just doing it now. So we're on the same page. Stop me if you have a question. But to my mind, this is the unit circle, right? It's centered at the origin. It has a radius of 1. Therefore, it intersects the x and y axes at those particular points necessarily. And theta in the unit circle always refers to an angle that's drawn between some arbitrary vector, some arbitrary radius, and a radius that lies along the positive x-axis, or in other words, in the first quadrant. So this is positive x, this is positive y. So this is the unit circle as far as I'm concerned. Okay, so there's my step 1 DFP. Okay, and then step 2, what's the question? Well, for A, the question is, what is the cosine of 0? And I'm just going to write it like that. I'm assuming from now on, and for the rest of our life in this class, we are always in radian mode. We're everything is about radians now. Okay. So how do I answer that? Okay, so I'm being asked the cosine of 0. Of course, I could just type it into my calculator, but like but how did my calculator know? So step 3, GDP. I think the big GDP of the unit circle, the big principle here is that at theta, the coordinates by definition are cosine of theta, sine of theta. Like the whole point, and I think you know this, the whole point of the unit circle is that whatever angle you're talking about, wherever that angle intersects the actual circle itself, the x coordinate of that point of intersection is known as the cosine of the angle, and the y coordinate is known as sine. Like as far as I'm concerned, that's the definition of cosine and sine. The x and y coordinates of where an angle cut out of a circle like this would hit the circle itself. Okay, so my GDP is in fact in the diagram. So for this case, so step 4. For principal application and work, for a particular application and work here. And I'm obviously, again, I'm doing this once to show you my thinking. And then for the rest of the exercises that are similar, I'm not going to repeat all of this. I'm just going to say the answers, and you're going to stop me when you don't like one of the answers, or when you're confused about something, or even when you're like, I get the answers, I already knew this, but I don't understand what this has to do with masses on springs or whatever. That's when you're going to stop me. But we're just getting on the same page here. So step 4 PAW is here in this case, the angle that we're talking about is 0. So the x coordinate is 1, is positive 1, and the y coordinate is 0, right? Because I'm just looking at my picture. If I'm looking at an angle of 0, I'm looking at the angle right here between the red line and the, maybe that's the clearest way I can do this. From now on, this should be always a red line. Right? If by angle we mean the interval between the black arrow and the red arrow, in an angle of 0, we're talking about the black and red arrow being one on top of another. So the x coordinate is 1, the y coordinate is 0. So I think the answer here, so I think the answer for the first one, and of course I've dragged it out, is that the cosine of 0 equals 1. Now, so that's my answer for that. Now, for the rest of them, you don't have to drag this all out, right? But the point is, can you get these answers by looking at your picture, not by punching into a calculator? Okay. And right now, this is a pure mathematical exercise, right? We're just making sure we understand the unit circle. Sorry, I'm going back to the page. We're making sure we understand the unit circle. And really secretly, I guess, what we're really trying to do here is make sure that we actually understand what radians are. That's really what's going on. So I'm going to do one more answer, and then I'm going to pause for a second to try to expand this radian business, which people are still asking me about. I mean, some people are still asking about. So, but I think that's the answer. So if you're just checking answers or making sure you did it right, or you want to know how to get full credit on the homework, I would say what I just did was like the fullest optimum version of what you might have done on part A. Now for part, that's the optimum version. Now in part B, from here on in, for diagram and definitions, please see above, like you can say that, please see above. So if now the question, so from here on in, so the question is, what's the cosine of pi over 2? Right, I'll cut to the chase. And I will say, I believe the cosine of pi over 2, I think I can look at the picture. And this is what we want to get ourselves used to, is without punching into a calculator, I can look at the picture. Well, and okay. I would say, what is the picture now? The angle that I'm talking about now, pi over 2 radians, is this angle here. Like you have to know that. And I'm going to pause in a moment after I get this answer and expand on that. But yes, this is assuming that you understand, or that I understand, that when someone says pi over 2 radians, what they mean is a right angle. And I want to explain why that is in a moment. But assuming that I do know that this is a right angle, then it seems to me the cosine of pi over 2, right? So this is the angle, right? Then cosine of pi over 2. Actually, could I just ask you, given all that, just to make sure we're still together and so I'm not boring you to tears, just put in the chat right now, everybody, just anybody and everybody, put in the chat what's the answer to this one. Just so and it'll also encourage me to go faster, which I'm sure many of you want me to do. Just put the answer to what this is. B of homework 2, cosine of pi over 2. What is the answer? Awesome. Oh, and some people are in the direction. I'm going to wait till there's a bunch of answers. I just want to make sure we're all together. Cool. Keep going. Even if someone's already written it. Cool. Because I didn't say it was right. I'm just saying it's cool that it's there. But give me one more, just so I can feel like I'm a teacher. Just give me one more. Somebody, what's the answer to this? What is cosine of pi over 2? Thank you. Okay. Thank you for saving this figure. Okay. Yes. And person in direct chat who was very, very fast, you were totally correct. And Alex, thank you for being so fast. And yes, you were all correct. The answer is 0. So the answer to this one is 0. And the way you would show it is with a diagram. The thing to know here the thing to, like, again, I'm trying to emphasize with the unit circle, like, you don't need a calculator to do these. If you understand how to draw the unit circle, if you understand that cosine is the x coordinate, you understand that y is the y coordinate, then the only thing that's left to be understood is how do you think in terms of radians? Okay, that's why we're here now. I will say right now, learning to think in radians is possibly what, it's technically a prerequisite for this course, technically, but nobody's kidding anybody. No, very few people are comfortable thinking in radians when they come into this course. If you get anything out of this course, hopefully one of the things that people do get out of this course, but at some point, is they start getting comfortable with radians. Let me pause. So I know I've said it before. I'm going to say it again right now. I'm going to pause. One. What is a radian? Oh, hello. The question is, what is a radian? I'm not going to do a whole, don't worry. I'm not going to spend hours on this right now, but I'm going to spend a couple of minutes. What is a radian and what does it have to do? What does it have to do with the physics of oscillation? And here's the answer. Okay, so that's my question. Like, why are we suddenly in radians? Radians have to do with angles. First of all, how do they measure angles? Third of all, what do angles have to do with the physics of oscillation? Well, here's the deal. A radian is a unit of measurement for an angle. And the key point here, and the reason we're emphasizing the unit circle so much, is an angle from here on in your life. An angle does not equal the space between two converging lines. Everybody in the world, when they think angle, they think something like this, and they think big angle means lots of space between the lines, and they think small angle means small amount of space between the lines. I'm not saying that's wrong, but I'm saying that's totally unhelpful. That's what gets everybody into trouble. What an angle actually is not space between lines. An angle is a fraction of a circle. That's what an angle is. An angle is a fraction of a circle. To say that one angle is bigger than another is to say that one interval is a bigger fraction or section of a circle than another. And the thing about circles is that you can talk about fractions of circles without having to know how big the circle is, right? Remember, and so an angle is a fraction of a circle. Remember that for all circles, the circumference around an entire circle equals 2 pi times the radius of that circle. C stands for going, right? C is measured in meters. R is measured in meters. What we are saying, when people talk about pi or 2 pi, it's very easy to get all caught up in the weirdness of the actual number. It's 3.14159. It goes on forever without repeat. I can't express it as a fraction. Like, that's all fascinating. But that's all fascinating in a whole different way. And it's so fascinating that it intimidates and distracts everybody from the actual issue. The actual issue is not whether it's easy or hard to express the exactness of the number pi. That is not the issue of pi. That's not the fundamental first and foremost issue of pi. The first issue of pi is just that it is a constant at all. What we are saying when we talk about pi or 2 pi, what we are first saying is, if you go to any, and forgive me if I've said, some of you I've said this to in my office, and some of you have made great, insightful inferences and associations with this point in my office. So please forgive if you're about to hear it for the second time. But because some people have done so well with this point in my office, I'm going to say it to all of you. Then forgive me if you're hearing it for the second, or forgive me if I've said it in class before. But here's the deal. If you go to any tree in the forest, I don't care if it's a small trunk tree or a big trunk tree. If you take a string and you wind it around the whole tree, right? So you take a string and you wrap it around the tree, and then you unwind that string and you put it down on the ground and measure how many meters long it is. That's called the circumference of the tree, right? It's the length that you'd have to walk to go around the whole tree. Now, some trees have big circumferences, other trees have small circumferences. The circumference could be any number of meters, and it could be a whole number or a fraction. I don't know. But then, if you cut straight across the same tree, if you cut straight across the same tree, and you put a string across from one point to the other in the tree, from opposite sides of the tree, and you put that string down, that's called a diameter. Cut it in half, it's called a radius. If you put the radius, or whatever, if you put either of those straight across strings next to your circumference string, the ratio between the two is always going to be the same, regardless of which tree you picked. Like the number of times that you can fit a radius into a circumference, that is the same number of times, no matter how big the circumference or the radius is. That's not obvious. That is not, I mean, wasn't born knowing that fact, right? That to go around a whole tree, it turns out, is a little bit more than 3 times longer than going straight across the tree, regardless of what tree it is. That's, I don't know that nature had to be that way. And especially once you realize that it's a little bit more than 3 times, that the string that goes around the whole tree is a little bit more than 3 times the string that just goes straight across the tree. It's just enough more than 3 times that it's hard to know exactly how much more than 3 times it is. So it takes a while to realize that no matter what tree you've picked, this ratio is always a constant. We call this ratio pi, between the circumference and the diameter. Therefore, we call the ratio between the circumference and the radius 2 pi. The significance of 2 pi is it is the ratio of circumference to radius of any circle, no matter how large. Thus, we can look at circles and we can say, like is in the example that we just did, we can look at a circle and we can say that if I go like this to a circle, that is an angle, right? I mean, you could see that is an angle. That angle is a fourth of the circle. Like what I'm recognizing in that shape, this kind of angle right here, if you recognize that right away as a right angle, which I'm sure you do, right? I don't care what number you put to it, but you recognize that 2 lines that are like that make the 2 lines that are perpendicular make a right angle. When you recognize that, what you're really saying is, I don't care how long the lines are. I don't care how far apart Yaverbaum's fingertips are from Yaverbaum's wrist, right? That is a right angle. Even if Yaverbaum used his arms or Yaverbaum just used his fingers, it's a right angle. So what are you seeing? You're not seeing a distance. It's not a distance. Like the distance could be really big or it could be really small. What you're seeing is that shape that you call a right angle or you call perpendicularity is a quarter of a circle. Just like right? And so you could call that 90 degrees if you want, or you could call it perpendicularity, or you could call it what the Greeks called it, which was just a circle fourth. You could just call it a fourth of a circle. That's what you're recognizing, that it's a fourth of a circle. Just like my son knows from Fortnite what a 360 no scope is. I don't even really fully understand what that is, but he knows what a 360 is. He knows the angle 360. Does he understand degrees? No. Does he understand radians? No. But he knows what a 360 is. And he's not thinking about lines when he thinks about a 360 no scope. He's just thinking about someone making a full cycle or circle around themselves. So therefore, my son knows just enough math that if I ever said do a 180, he would understand that's a half circle. And if I say do a 90, okay, that's a quarter circle. Now here's where I'm going with this. The 90, the 180, the 360, those are just arbitrary numbers that you've learned from Fortnite or from second grade or whatever, because we decided at some point in history to divide a circle up into 360 parts. There's reasons for doing that, but they're not particularly helpful or convenient when you're doing a geometry problem or you're on paper or you're doing physics in the lab. What is convenient is to recognize that, like, this angle is a fourth of a circle, right? An angle is a section of a circle. An angle that's bigger than another angle is a bigger section of a circle. How do we measure sections of circles? The easiest way to measure it is literally how much arc length you get, like how much crust of a pizza you get per each unit of radius for that pizza that you cut the slices out of. What I'm saying is this. I'm saying that what an angle is it's not a distance between two lines. It's an arc length between two lines, but it's an arc length that we all agree to cut when the two lines are 1 unit long. Like, we all know that if we made the circle twice as big, we'd get twice as much arc length for that angle, but we still want to call it the same angle. So we say, okay, just as once you measure out 1 unit radius, how much arc length do you get for that? That's what we mean by an angle. What fraction of the circle do you get? So literally, it's arc length divided by radius for a whole circle. This is what an angle is measured in radians. A radian is a pure way of measuring angle that's just literally reducing an angle to its fundamental meaning, which is the section or the fraction of the circle. So for a whole circle, for example, you know that for a whole circle, the angle going around a whole circle would be the full circumference, would be the arc length, all the crust entirely of the pizza divided by the full radius. So therefore, and here's my takeaway, and I'll go back to the homework in 1 minute. But if there's anything to understand here, is that from now on, if you're trying to understand what is a radian, here's what a radian is. The angle which takes you around a full circle, right? What we used to call 360 degrees, is 2 pi radians. The big, and I do apologize if I've said this a million times, but the big conversion factor, the big connection between all of this circle geometry, trigonometry, cosine, sine crap, and what we're actually trying to do in the lab of looking at something going back and forth, is that all of this is about circles and all of this is about cycles. And what we are saying from now on is one full cycle is called mathematically 2 pi radians. 1/2 cycle from now on is called pi radians. 1/4 cycle is called from now on pi over 2 radians. Okay, so to bring it back to the homework, how I knew that this was pi over 2 radians is because this is a quarter of a circle. A full circle is 2 pi radians, so half of it is pi, so a quarter of it is pi over 2. And lastly, I'll say, therefore, if this is all true, and then I will go back to the exercises, but this is a conversion. So, well, yeah. So if someone says from now on, it's got an angular frequency, this oscillator has an angular frequency of 2 pi radians per second, I know how obscure that sounds. It doesn't just sound obscure to you. It sounds obscure to all of us to say something as something going back and forth like this has an angular frequency of 2 pi radians per second. Like there's the word radians in there. There's the word pi in there. There's the word angular. Like what the heck does any of that have to do with something going back and forth like this? And the answer is if something's going back and forth like this, if it has an angular frequency of 2 pi radians per second, what that means is it's doing 1 cycle per second. That's what we're talking about here. 2 pi radians equals 1 cycle. Actually, I'm going to stop right there. Hold on. I'm going to stop right there for a moment. I know if I'm going to yell this much, just give me. Oh, and there's T. Oh, welcome back. Okay. So if raise your hand if you're with me so far, whether you've heard it a million times or not, is it clear that 2 pi radians means 1 cycle? Is that clear so far? Well, thank you, Madonna. Thank you, Josh. Thank you, Tiggy. No, it's not clear. Wait, is it? Thank you, Mohammed. The question to everybody right now, before I go on, since I'm yelling so much, is it clear that from now on, when we say 2 pi radians, we mean 1 cycle? Okay. Oh, thank you, Madonna. Wait, but guys, help me out here. I'm dying. I'm going to say it one more time. Okay, no, I'm going to say this. Raise your electronic hand or somehow acknowledge if you hear me speaking right now. Thank you, Madonna. Thank you, Emily. Thank you, Mira. Thank you, Tiki. Okay. Thank you, Sadie. Now we're talking. Thank you, Tiger. I got 2 thumbs there. Thank you, Roland. And thank you, Luigi. Let's go. Thank you. Okay. So now I'm going to repeat my question again. And I'm sorry to do this, but if I'm going to yell this, and it is a big point, okay? And I think it really does help some of you. I mean, whatever. If I'm going to yell this much, it's got to land somewhere. So now raise your hand. You can put your hands down now. Thank you, including, I love the Luigi thing. Sorry. By the way, of course, the only 3 movies I've seen in the last 10 years, literally in the theater, I believe in the last 10 years, maybe more, the only 3 movies I've seen in the theater, just so you know, are, of course, obviously Oppenheimer, and of course, obviously Barbie, which I thought was better, but okay, whatever. And the Mario movie, just so you know, those are the only 3 movies I've seen in the last, and they were all worth it. But okay, but yeah, Barbie was better. Okay, so wait, so do you? Not okay. Okay. Anyway, raise your hand if this is this clear. 1 cycle equals 2 pi radians. Is that clear? Yeah. All right. Okay. Tiki's vote is going to count for 2 people. At least 1 person doesn't have to raise their hand because she raised 2 thumbs. Okay. All right. Okay. Montserrat, thank you. Emily, thank you. Roland, thank you. Mira, thank you. Madonna, thank you. Josh, thank you. All right. That's good enough for me, I guess. All right. Because now I'm going to go the flip side, and then I'm going to go back to the homework. I know we're just going to blast through the homework then, if that's really clear. But then if that's clear, I'm going to say the flip of that, which often people don't realize. That means if from now on you're ever wondering, okay, like a lot of people then think, well, fine, I get it, that like, I get that a cycle is 2 pi radians, but that still doesn't really tell me what a radian is. Like if you just say radian, like what am I supposed to picture when you say radian? Like what? Well, here's the thing. If when I say degree in terms of angles, presumably what you picture is a 360th of a circle, right? Like honestly, right? Like angles from now on are fractions of circles in math. In physics, therefore, angles are fractions of cycles. Again, get rid of the idea that angles are like bent shapes or turns or curves. They're not. Angles are fractions of cycles from now on. So if I ever said 1 degree, like as in a turn, like as in a snowboarder doing, or like a motorcyclist or what, an acrobat doing this. If I said they didn't do a 360, but they did a 1, like which would be pathetic, you would think, okay, I guess they turned their body like 1/360th of the whole way. And that's pathetic. So I'm not hiring them as a stunt person or whatever. So from now on, similarly, if I ever say radian, what you want to picture as a radian, what a radian is 1/2π of a cycle. Okay, and what does that mean? Well, really, what that means is approximately 1/6 of a cycle. Approximately. If you're just trying to picture, why'd I get 6? Because pi is basically 3. To a physicist, to a mathematician, maybe it's exactly 3.14159, blah, 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 blah. That's fascinating. To a physicist, pi is basically 3. So 2 pi is basically 6. So if anybody ever says radian from now on, and you're trying to picture what the heck I'm talking about, a radian is a 1/6 of a cycle. It's that simple. It's that straightforward. A radian is a sixth of a cycle. If I say someone had an angular frequency of 60 radians per second, I'm basically saying that they did, well, that was a stupid. If I say that they did 36 radians per second, I'm basically saying they're doing 6 full cycles per second. That's what a radian is from now on. That's all I can say about it for the moment. And so therefore, if someone says there's a fate, because someone was asked, 2 people asked me about this in the homework, that whole fee thing. I mean, I'll get back to it. I know it's disturbing people if I'm like too far away from the homework. I reckon it. So I'll go back to the homework in a second for organizational sake. But like for those of you who are like still confused about phi or phi, whatever, that term, that extra phase constant term that's in the cosine function, that thing is a head start or delay, measured in terms of radians. Right? I mean, it's technically called the phase shift. But so from now on, for example, if that thing equaled pi over 2, that looks like, what does that mean? But if that thing, phi, equals pi over 2, then that means the oscillator wasn't all the way at the edge of the cycle when we started our stopwatch. It means it was already a quarter of a cycle into the cycle when we started our stopwatch. It means specifically then the oscillator, then mass, then the mass was at equilibrium at t equals 0. If this were a bigger point, I'd put it on the next page, but it's that's sort of a side point anyway. So if you don't totally need that or get that, it's okay. But all right, if there's no, I'm going to go back to the homework because I'm sure I'm losing people here. But I'm going to go a little bit faster now because I think. So back to the homework. We're back to homework 2, and we're up to, Roman numeral 1. We've done A and B. Now I'm just going to do answers now. I'm not going to do all the 5-step method and everything. Stop me if you don't like any of these answers. But I'll like the questions, but I'm not going to. C, cosine of pi. Pi is half a cycle, so I'm looking at half the circle. I believe the answer to that is -1. Stop me if you don't like it. And I don't mean that as a threat. Then cosine of 3 pi over 2. I believe that's 3/4 of a cycle. Right, so it's down there at the bottom. I believe the cosine of that is 0. Sine of 0, I believe is 0. F, sine of pi over 2 means sine a quarter of the circle. So we're up at the top. The y coordinate is 1. If nothing else, note this. Like obviously, I'm not looking at anything when I do this, right? I'm not doing this on a calculator. And it's not because I've memorized these, and it's not because I'm so smart or something, because I'm not. I'm smart, but so are you. It's because I'm just picturing the unit circle in my mind. And in my mind, what I've gotten used to is if someone says pi over 2, I picture a quarter of a circle. If someone says pi, I picture a half a circle. That's what I'm trying to get. And that is not beyond any of you to think that way. So I guess what I'm really trying to say is I'm not. The thing, if you already got these correct answers, which a lot of you did, and like you want to move on, which I totally appreciate, like the thing you want to be asking yourself is, are you getting to the point where you don't have to translate these things into degrees anymore in order to get it right? Like that's your goal. You want to be able to do these not on a calculator, and you want to be able to do these without doing the extra step of translating into degrees. That's the goal. So that's what I'm doing right now in front of you. Like G, what's the sine of pi radians? That means I'm going a half a circle, but I'm asking the y coordinate. So the sine of pi is the same thing as the sine of 0. It's 0. H, and then I'll go to the next page. Sine of 3 pi over 2. Is -1 because that's 3/4 of the way. That's 3/4 of the circle down to the bottom. All right. So that's. That's the answers to those. Again, stop me. I'm going to just keep going unless you stop me. All right, I'm going to keep going. Hold on, I'm also going to change the view on the screen, pardon me. Now, with these, well, I'll just say the answers first of all. So now I'm in 2. A is cosine of pi over 4. All right, I'm going to pause for a second. Well, no, I'm going to write I want you to flag these. Those of you who are still paying attention to me, work, bless you. Those of you who are still paying attention, I'm going to give the answers to these because I know I should just keep moving. But I want you to flag this section because there's a reason we do this section. Like you notice these numbers are now a little bit harder. They're a little bit harder to, in fact, they're substantially harder. You might know these answers, you might not, but these, to just eyeball these, like now we're going, in between the cracks. Like now we're asking for numbers that are not at one of the obvious 4 points. So there is something going on here. I want you to flag this. If we have time, we're going to go back and I'm going to show you really how to make the diagrams that this is asking for. And I really want you to flag this because I'm going to promise you right now, if these kinds of things are on the exam, if they are, then I'm going to expect you to draw an actual diagram to actually justify these answers. It's not good enough to just get it from a calculator. But that means I would have to teach you that. And that will be dependent on the time. So either I'm going to teach you it and it's going to be on the exam, or it's not, or I'm not, and it won't. We'll see how much time we have, but I want you to flag this. And it is at some point, one of you is going to say to me, hey, by the way, like now that we're talking about the exam, are you going to put funky angles like that on the exam? Yes or no? Okay. And it's going to be and again, I'll be fair. If I don't teach it, I won't put it, but we will make a conscious decision about that. So please flag these or I'm sorry, just raise your hand right now if you understood what I did. Hold on a second. I got to change the view on the screen. Do you understand what I'm saying? Could you raise your hand if you understand that I'm asking you? Okay, that's good enough on that one. Thank you, Madonna. That's good enough. Okay, but so here are the answers for now. Thank you, Madonna. I totally appreciate it. And I'm not being, and thank you, Sebastian. Oh, and thank you, Taco Robin. Thank you, Angela. Okay, I'm not being sarcastic. Thank you. All right, so now, but I am going to give you the answers for right now. I believe the cosine of pi over 4 is radical 2 over 2. Oh, and it says, and I'm going to say this. Just to be clear too, sometimes on the exam, we make a big distinction. Sometimes on the exam, we make a big distinction where we ask you in some contexts, to provide us with exact answers the way mathematicians would. And sometimes we ask for approximate answers, not because we're trying to be cheesy, but because as physicists, as scientists, the only kind of numbers we ever deal with are numbers that you could get from measurement. And the only kind of numbers you can get from measurement are intrinsically approximate numbers. They're not exact. So you're never going to measure like the exact square root of 2. What you're going to see on a meter stick or square root of 2 divided by 2, you're not going to see 1.414, blah, 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 go on and on repeating. On and on forever without repeating. What you're going to see on a meter stick is something like 1.414, or in this case, 0.707. So I'm just alerting you that that's also a distinct, you have to be careful whatever the instructions are on the exam. So if we're asking for an exact answer, the answer would be radical 2 over 2. If we're asking for a measurable answer, it would be approximately 0.707. Okay, so that's the answer to that one. And then for B, sine of pi over 6, the answer to that is 1/2, no matter what. We're going to the next page. Tell me if you want me to go back, but C cosine of radical of pi over 3. In other words, a 12th of a circle. A 1/6 of a circle. So that's 1/2. And the sine Oh, and again, with these, ideally you would do the 5-step method for like the first of them, but then after that, you wouldn't have to repeat every time. Sine of 5, 6. And that's -1/2. So those are the answers to those. Okay. Again, if there's, I'm just going to move on. Okay. I'm just going to, if there's no questions. Okay. I'm going to move on. Now so that was all like the math setup. That's trying to get you to really, that's just trying to grind into our brains how the unit circle relates to how the unit circle relates to angles, how angles relate to radians, and how radians relate to cosines and sines. So that's the math, right? So the whole idea now is that in our brains, we have this mathematical way of analyzing circles. So then we go to the physics now in the next problem on the homework. On the next, we now get to physics, and now we start looking at something that's oscillating, that's undergoing cyclical behavior in space and time, right? So, so here's a diagram. So I'm definitely, so now we're on problem 3 of homework 2. Here, I would definitely do the 5-step method. Right? For those of you who are very legitimately concerned that some of those exercises don't seem to lend them. Oh, and I think, to be honest, also, I know that some of the people that have asked about that, they were actually asking it about homework 3 as well. And totally fair. But here's the deal with this one. I definitely think this is a 5-step method kind of situation. So first, I'm going to draw a terrible diagram. We've got a door going back and forth. I am not the man for the job on the. Oh, I'm going to do it. But if anybody's still paying attention, if anybody right now wants to either produce a drawing of a door closing and opening, or if they have one in their notes that they want to screenshot, and it would be great if anybody wants to put that in the chat. There's about 1 million portals you could then submit for extra points for putting up image in the chat. And 2 people already did put images in the chat today, and they should definitely submit for points for those. But if you could put an image of a door opening and closing, that would be awesome, because I certainly am not going to do a good one. I mean, I can't even imagine how. Well, here's the door, and going back and forth somewhat ridiculously. And it is a barn door, right? Why? Who cares that it's a barn door? Because the whole idea is that the barn door, can swing in both directions, right? Which again, I have a hard time drawing, but just like a mass on a spring can extend and compress. That's the idea that we're picturing here. So swing fully out. Okay. And what's given is that the angular frequency here is 628 radians per second. So this is all what's given in the problem. So this is my step 1 DFP. Okay, right. This is and I'm just looking to see if anybody did this in the chat. No. Okay. All right. So step 2, what is the question? And the question is, Okay. Okay. That's the question. It's like, how many cycles per hour does this barn door make? And this is an exact extension of everything I was just like yelling about at the top of my lungs. Because what it's asking you to do is now start converting in your mind from the concept of radians in a circle to cycles in physical space, right? And that's the whole idea here. And really the whole thing comes down to one cycle equals 2 pi radians. That's what all of this comes down to. But if you want like a formulaic or equation-y way of anchoring that in your mind, the step 3 GDP for this, okay, is this. And I can't remember. I think I said this in the video a couple of times, but I don't think I've said this live to you. Is this. Well, okay. Here we go. Wait, I'm going to do this on the next page. This is long enough. Pardon me. I'm doing step 3 GDP all on the next page because I'm going to lay out 3 equations for you now that may, or 2 that might clarify things for some people. Right. So omega is angular frequency, right? Which means how many radians per second you're doing. Well, if that's true, from now on, lowercase f will stand for not angular frequency, but the thing that we really would more sort of care about as normal people or as scientists or people not dealing with circles on a piece of paper, but cyclical behavior in space and time. What we would care about is what you might call standard frequency, right? Standard frequency, the units, and whenever I put square brackets around something, I'm talking about the units in which it's measured. So the units of omega were radians per second. The units of standard frequency would just be everyday, regular, standard cycles per second, right? But now what you may have already picked up from a video or from Professor Moses or from life is that there's a name for sorry, and notice there's a name for a cycle per second. There's a name for that unit. 1 cycle per second in science is called 1 hertz. So from now on, when we talk about standard frequency, the units that we're talking about are hertz. A hertz is a cycle per second. When they say you're tuning into 105.9 megahertz on your FM dial, like radio station, right, or whatever you're listening to, if they say 105.9 megahertz, they mean something is cycling at a rate of 1,000,000 cycles per second. Like mega means million, hertz means cycle per second. So 105 or whatever, whatever you listen to, 105.9 megahertz means 105.9 million cycles per second on your FM dial. FM stands for frequency modulation. Modulation is to change. So, okay, so what they're talking about there is something cycling at a certain rate of frequency, standard frequency. Standard frequency is measured in hertz, cycles per second. How do you get back and forth between angular frequency and standard frequency? Well, it's exactly what I've been yelling about for an hour and a half. the whole idea is that one cycle is equal to 2 pi radians. Therefore, if you just want to memorize or to reduce this whole thing, you may already have it in your mind. In the end of the day, angular frequency is simply 2 pi times standard frequency, i.e., i.e., something measured in radians per second is equal to 2 pi radians per cycle. Like there's 2 pi radians in every cycle, right? Times cycle per second. It's just a unit conversion, if you like, right? You can memorize. I mean, I remember memorizing this and just memorizing it and having no idea like what it meant. So fine, if that's what you do. Omega equals 2 pi f, or you can write similarly, f equals omega over 2 pi, same thing, right? It's just saying that there's 2 pi radians to every cycle. But I'm going to go one step further now, as long as I'm giving you equations. But that's an equation you can memorize if you like, whatever. But you can go a step further and realize standard frequency. Yeah. You can go a step further and go back to the stuff that we're always actually having an easier time measuring in the lab and picturing in our minds. There's this idea of capital T period, which means, well, period. And what does that mean? Period means the amount of time it takes to complete a full cycle, right? So period is measured in seconds per cycle. Oh, notice that. Standard frequency is measured in cycles per second, right? Standard frequency is measured in cycles per second, but period, the thing that our whole entire class, like lab 1 was all, and lab 2 were all about, like focusing your attention and all your measurements on the period of some oscillator. Period is how much time it takes to do a complete cycle. So period is measured in seconds per cycle. In other words, just to make this as explicit as possible, right? Period is in seconds per cycle. So to make this as explicit as possible, what we're saying is that period, by definition, is just the reciprocal or the multiplicative inverse of standard frequency, right? It's just the flip of it. In English, if I know that I run okay, I'm gonna warn you right now, just to make sure everybody's still with me. Just to make sure everybody's still with me, I'm gonna ask you a question. It's not in the homework. It's just to make sure you're with me. It's not a trick question. It's just to make sure everybody's with me. Cork, forgive me. If my frequency of running laps around the track, I'm running laps around the track. My frequency, let's say, is 4 laps every hour. Like 4 laps per hour, let's say. If I'm running 4 laps per hour, what is my period? That is to say, how much time does it take me to do 1 lap? I'm going to repeat that. I want you to respond in chat, ideally direct chat. I'm going to wait until I get at least 3 answers in direct chat. I'm going to repeat the question now, but I'm not going to move on until I don't care if the answers are right or wrong. Or you could say in the direct chat, like, I was totally spacing out. Can you like back up? Whatever. But, I think there are some answers already. Oh, there's at least one. Thank you. There's at least one answer in the direct chat. I'm even going to say that person is correct. That's awesome. Thank you, direct chat person. But I'm going to repeat the question until I get 3 answers in direct chat. It's not a trick. It's just a wake-up call. If my frequency is 4 laps per hour, I do 4 laps around the track per every hour. That's my frequency. Then what is my period? I.e., how much time does it take me to do 1 lap? If I'm doing 4 laps per hour, how much time does it take me to do 1 lap? I see another thing in the direct chat. I'm looking. Awesome. Awesome. I just got 3 things in the direct chat, 4 things in the direct chat, 5 things in the direct chat. I love this part. 6 things in the direct chat. Oh my God. And they're all in the direct chat, so nobody knows. But I'm even going to say that they're all correct. I'm so excited. So maybe that will, of course, if I were in the class and I hadn't responded yet, that might intimidate me more. But I'm not saying what the answer is, but I'm just saying I've got maybe 7 answers now in the direct chat. 1, 2, 3. All right, you're totally with me. 4, 5, 6, 7. And all of them are correct. So I'm not going to push my luck. I'm going to retire now. Thank you. I'm going to take out my 403B or whatever, which has nothing in it. Great. Yes. And what you all said, actually, this may be the first time this has ever happened in class. Like literally 7 of you all responded. You all responded to the direct chat and you all responded correctly. That means I'm going too slow and the exam is tomorrow. Just kidding. No, that's awesome. But maybe I am going too slow. You could tell me if I'm going too slow. But yes, okay. The answer that everybody put in the direct chat was they either wrote 15 minutes, which is correct, or they said like 1/4 of an hour, which is like literally, yes. I mean, both are correct. Like if you do 4 laps per hour, then your period is 1/4 of an hour per lap. Absolutely. So therefore, the summary of all this, it really seems like I can go on. Maybe I am dragging this out. I apologize. But at least I'm yelling, so it's exciting, right? Just kidding. But what this means is, in sum, we have W equals 2 pi times F, if you want. And we also have W equals 2 pi times T. I'm just summarizing. You can memorize, they all mean, what this means in the end is, just to be clear, from now on, the bottom line is this, and then again, I will return to the homework. All the homework is just an excuse to teach anyway. What I'm saying is from now on, omega, i.e. angular frequency, F, i.e. standard frequency. Oh, and by the way, I'm using F. If you ever go on websites or in books, a lot of times books and websites will use this lowercase Greek letter nu, which kind of looks like a little V. I don't use that partly because it looks too much like a V and it's whatever. But if you ever see that they mean the same thing as when I use F, they use that for standard frequency. So angular frequency, standard frequency, and period are all 3 completely interchangeable ways to measure one and the same thing, which is cycling rate of cycling. If you know one of those, you automatically know the other 2 because you use any of these equations that I just like wrote down right here. You can convert back and forth among all. If you know one, you automatically know the other 2. So please understand that they're all interchangeable. So then if you ask, well, then why that? I mean, typical physics, if they all mean the same freaking thing, why do we have 3 of them? Fair question. But the reason is this. Omega is what's spit out by the math. Omega is what the math of cosines and sines and all of our mathematical functions that we need to be precise, it will spit out things and think things in terms of radians and omega. So omega is the mathematically direct way of thinking about this. Capital T period is the experimentally direct way of thinking about this. Like for all of us, if we're in the lab and we want to make measurements, absolutely the easiest thing to measure and to picture in our mind is period for all of us. So period is the most physical, you could say, the most tangible, the most physical. Omega is the most mathematical, and F is the bridge between the 2, just so you know. Okay, I mean, that's the way I think about it. So that's that. So now to go back to the homework problem then, unless there's questions, which there are not. So back to the homework problem. I'm basically going to just use those equations that I just developed. I mean, and again, all of it just comes down to saying there's 2 pi radians to every cycle. So in the homework, I think omega was given as 628 radians per second. So now I got to convert this into an F, right? And I've got to convert, we want F, but we want it in cycles per hour. So I have to take that into account eventually. But the first thing I'm going to do, the first thing I'm going to do, I can't remember. I feel like this came up already. Maybe it came up with someone in the office. I'm going to do something that you may or may not have done. I'm going to use a little insight here. You didn't have to do this in your homework if you didn't do what I'm about to do, but what I'm going to do is I'm going to look at that number and say 628 radians per second. That's a bizarre number for someone to pick. Like, why would they pick 628? What I'm going to recognize in my mind is, oh, you know what? I don't think that's a coincidence. 628 sounds a lot to me like 6.28. In other words, when I look at that number, you don't have to do this. But to me, my life is a lot easier if I look at that number and I say, note, 2 pi approximately equals 6.28, right? I mean, pi is like approximately 3.14. So it seems to me that that number secretly, what it's really saying is 200 pi. Oh, yeah. It seems to me that I could right away convert that number and say 200 pi radians per second. You don't have to do that, but I feel like if you can make that recognition, that's sort of cool. And I know that F is omega divided by 2 pi. I just, because of this right here in the middle of the page. Here. If omega equals 2 pi F, then F equals omega over 2 pi. But really, so you can memorize that if that gives you more sense of security, but really, just logically, I'm saying there's 2 pi radians in every cycle. So if I want to know how many cycles, I'm dividing by 2 pi because every cycle constitutes 2 pi. So it equals 200 cycles per second, right? This frequency, in other words, if the problem had asked me what's the standard frequency measured in hertz, I would be done now. I mean, 200 cycles per second, I mean, that equals 200 hertz, just so we know. And that's a realistic number. But that's not what the problem is annoying. It is annoying. I kind of regret it, but the problem actually asks me to convert this into cycles per hour. So, okay. So if F equals 200 cycles per second, but I want it in cycles per hour, what I'm going to do is I'm going to multiply by 1, since that doesn't change anything. Well, I'm going to do this. You tell me. I mean, people do this all different ways, but I think that there is 3,600 seconds in 1 hour. Where did I get that? I mean, 3,600 is 60 times 60, right? So maybe I'm skipping a step, and stop me. If you have the guts, if you think I'm skipping too many steps in this, I definitely want to know, and I'm happy not to. I just don't know what people know or what they don't. But in my mind, there's 60 seconds in a minute and there's 60 minutes in an hour. So there's 3,600 seconds in an hour. I mean, that's in my mind. But the key point, you could break it down to more steps, but the key point is I knew, like when it comes to unit conversion, let me put it this way. What people are always confused about in unit conversion is they often know what the conversion factor is, and they often know they're supposed to sort of use that conversion factor. But what often people, even after chemistry class, the thing that gets people is I just don't know whether I'm supposed to multiply or divide, or at least that used to be my problem. I know the conversion factor, now I got to use it, but do I multiply or divide? The way, sorry. Oh, is it 100? I'm sorry. Oh, maybe you're right. Wait, I'm sorry. Oh, great question. I'm sorry. Someone in the direct chat, great point. And by the way, there's a portal, or I think I opened it. If I didn't, there's definitely should be a portal for if you correct a mistake of mine and you catch me. Definitely you should submit for points. Yes, someone in the chat who shall remain nameless, but thank you. I think you're right. Wait, I did 200 pi. No, you're absolutely right. It's 100. Thank you. Does it? Hold on. Thank you. So people really are paying attention. Thank you. Yes, 100. Thank you. Wait, just okay. Sorry, I hate to do this, but just raise your electronic hand if you just caught that correction. If you are aware that we just made a correction. Thank you, Madonna. Good enough for me. And raise it. Okay, good enough for me. Thank you, and thank you, Mira, and thank you Jamie and Ali Rod. Okay, great, and thank you for the person who gave me that correction. And I totally understand why they did it privately because that's so respectful. But yes, they deserve full. Yes. Okay. Wait. So now here's the thing for the just quick thing. When you're doing unit conversions, especially when things are in the denominator, for some of us, it's complicated. It's confusing whether we do multiplication or division. My trick for that is I always do multiplication. I always multiply by something that equals 1. Like I multiply by a fraction whose numerator and denominator are equal to each other, right? Like 3,600 seconds equals 1 hour. So it's like having 7 over 7 or x over x or 4 over 4, right? It's 1, right? So I'm always multiplying the way I do it. I always multiply. But I just decide how to write the fraction, whether I write the seconds on the top or on the bottom. How do I decide that? I just put the seconds wherever they need to be so that they would cancel out. Like here, I'm trying to convert from seconds to hours, right? I'm trying to get rid of the seconds. I'm trying to keep the hours. So I just deliberately put the seconds on the top here so that they cancel with the seconds that are already there and I'm left with hours. That's how I don't know if that helps anybody, but that's how I always do it. I'm always multiplying by some fraction and I always decide how to write the fraction by just looking at what I need to cancel out. I don't, if that helps, it helps. And if it doesn't, it doesn't. But anyway, right. So then we just say, okay, so the frequency is 3600 times 100 cycles per hour. And I think it would be better, crazy, stupid numbers like that are better to write in scientific notation. So I would say something like 3.6 times 10 to the 5th cycles per hour. And that's the answer. Go back to the last page. Yes, I'm so glad. So yes. Okay. So let me know when I'm going to look at the, so hopefully we're making some kind of progress here. I'm just looking. Okay. But just I'm glad someone asked me to go back a page. And by the way, there's a portal for that. You can get points for asking me to go back. But I'm glad someone did because it shows that we're still together. But let that person who asked me to go back. Oh, I guess it was public, right? So let me know when I can go back again. Yeah, I guess it was public. Okay. So let me know when I can, or if I'm in the right place at all. Great, thank you. Oh, and there's a portal for that. Now he told me I can move on. There's like triple, that's like 1,000,000 points right there. Okay. So we move back. Okay. Thank you. All right. So we can move. So hopefully we're making tracks now. We think, we hope. Yeah, I'll just keep going. Now I'm not gonna, by the way, also so you know, it's not like all the time in this whole class, we're always gonna go over every single problem that was ever assigned. Like that's not the case. I think we're still early on enough, and I think the rhythm gets interrupted enough by, not having class or whatever, that I'm just trying to get things as clear as I can right now for you. But we're not always going to do every single problem. But we will keep going for right now. Yes. Okay. I'm just looking how much is left. Okay. Okay. So that's oscillation in general. Now we're going to be even more specific. We're relating oscillation to the kind of objects we have in the lab. Masses on springs. So this goes back to like homework 1 now. Okay. So that's my step one DFP. Oh, well, okay. Also, all right, another given in this whole thing, sorry, it actually says a beat later that we're assuming, because now we spent all these weeks figuring this out, we're assuming that this expression describes the motion of an oscillator. Okay. So the first question is what is the angular frequency? Okay, I'm going to pause here now. Well, I'm going to pause. We need step 3 GDP to do this. We need some sort of general definition or principle. Do we know what? So I'm going to ask you now, and I don't know if this is this is not a trick question, but I don't know that we've ever said this in lecture yet. But from all the labs that you've been doing, not so much from this week's lab, but from the lab the week before, and possibly lab 2, does anybody in the room know how to get omega from the givens in this problem? In other words, well, so that's the question. So I'm going to pause and see. And I don't, well, I think you know it from labs, and some of you have done this homework, so but I'm going to wait. And you can go in the direct chat again. In fact, please do go in the direct chat. I'm going to wait, but this is not like a wake-up call. Like, this is actually, I think, a question that requires either thought or good notes or memory or something. But what we're asking here, like, we now know. What I'm trying to say is, I've just spent all these. Here, let me put it this way. Okay, so the things that are already in the chat. Wait, let me just look in the chat. What? Awesome. Okay, there's one person in the chat, in the direct chat. I totally agree with what the one person put in the direct chat. That's great, and thank you. And that one person has been very, very active in the direct chat today, so thank you, seriously. I totally agree with that person. I'm still going to pause for a second and see if other people know also, because this is important, and this is now, I'm not saying it's obvious at all. It's totally not obvious. There's no way we were born knowing this, but it is something that's, in principle, we've learned from the lab at this point. And I want to clarify too. So one person's gotten it right. That also does assure me that somewhere you've seen this somewhere. But let me make it clear that everything that we've been saying about, like, if you were to flip back your pages right now, or this were the middle of an exam, you'd see a million equations that we just derived for omega. And you might think like, well, how come can I use those? Like, didn't he just tell us what omega equals? Hasn't he been screaming about omega for 2 hours? What I've been screaming about for 2 hours is what omega means. And all those equations that I just wrote on the other pages, really, in theory, those really are triple equal signs. In fact, let me correct that right now if I didn't already do that. Really, like these equations right here, really, in the end, are triple equal signs because they're just expressing the meaning of angular frequency. They're saying that angular frequency is a cycling rate, and it's by definition related to other ways we express the cycling rate. What's being asked in this question? So that's math. What's being asked in this question right now in the homework is now we're relating back to physics. We're saying, if you had a mass on a spring of a certain amount of stiffness, could you predict the cycling rate in advance just by knowing what type of mass you had and what type of spring you have? That's what which is like a physics leap. So there's now 2 people in the direct chat. Awesome. Okay. And that made me 2 people seem to know where I'm going with this. Thank you. And they're both correct. Just for the sake of it, I'm going to wait for one more person, but then I'm going to call it like knowledge. If one person can give me in the direct chat, like, how do you get omega? I'm going to pause for a second too. Hold on. I'm going to wait for one more person. So the question is, what is omega? Double equal sign, not triple equal sign. How do you get omega from K and M is really the question here. Sorry, I'm coming 1 second too. Okay, sorry, so I just got to try. So I have now, okay, wait. So I now have in the direct chat, I have a bunch of things. Thank you. I have like 5 things in the direct chat, or 4 or 5, and at least 3 of them are the right. Okay, great. I'm going to be frank. So at least one of you in the direct chat is saying that omega is 2 pi over capital T. That is true. That is totally true. And it shows you're paying attention because I did write that a couple of pages ago. I want to make it clear that business, that omega is 2 pi over T, that is true by definition. But that's what's not going to help us here because I guess to be blunt, we don't have we don't know capital T yet. We could get omega if we knew capital T. But in order to get capital T, we would need omega. We would run in circles. I'm not saying that's, and so by the way, if you were in an exam, just to be super clear, if this were an exam and you were starting to solve this problem, if someone wrote down, let me make this very clear. If you wrote down as step 3, GDP, omega equals 2 pi over capital T, you would get points for that. That is not wrong. And it's very smart to write it down if it's getting your brain going. I mean, it's true. This is the whole nature of the 5-step method. If you're stuck and you write down something for step 3 that's true, then you get points for it. And especially because it's going to help advance you to, but you would still have to go further to solve this problem. 2 pi over 2 won't get you an answer here because we don't know. I mean, 2 pi over t, because we don't know t. But what a bunch of other people have written in the direct chat, and thank you, and you can all submit for points, please do. A bunch of other people have written down that while omega triple equals sine 2 pi over t, omega double equals sine square root of k over m. This is important now. Now this comes from lab. What you've done, it's sort of the purpose of ultimately of the first two labs is to come to realize this. This is a revelation now. And also I know I talked about it in the video, I think, but let's dwell on it for a second. Well, all right, I'm going to use this. I'm going to use this now just to finish the problem so we can keep momentum going. But this okay, so this, like, how we know this? It's easy. You spend so much time in the lab and you're doing so many things, it's easy to lose the forest for the trees. I want you to know that part of the purpose of everything you were playing around with in lab, really in lab 2, I guess it was, you're getting a whole bunch of data so that you can eventually satisfy yourself of some relation like this. Now, there's other ways of writing this relationship because of what at least one person said in the direct chat, and because of all this stuff that I'm yelling at for an hour and a half, like the way you might have seen this in the lab might have looked something more like this. You might have seen something like this in the lab. Okay, like that's how it might have altered. Like first in lab 1 or 2, you found out that the period was directly proportional to the square root of the mass. That's the first thing you found out in the lab. That period depends on the square root. That period depends on the square root of the mass. Then you eventually did this curve fitting stuff and whatnot to find out what the constant of proportionality actually was. And you found out that the constant of proportionality was 2 pi over the square root of k. It's very easy to lose this forest for the trees, right? And then now in this class or in other classes, we're saying, well, if you know the period, you can get from the period to the angular frequency, you just do 2 pi over it, like one person in direct chat was saying. So ultimately, what I'm saying is, even if it didn't look that way in lab, what the purpose of some of your lab work is to find out this relationship, which is not otherwise obvious at all. It's not something you're born knowing. It's also something that if you want to mathematically directly verify or directly prove, like if you don't trust any of your data lab, the truth is it's fairly straightforward to show that this is true using calculus. But we're, just so you know, like there's other ways also of verifying why we believe this. We don't just believe like 5 sort of rough points on a Desmos graph, but so it's also from calculus for those of you who care. But that's not required for this class. What I know is that double equals sign, it turns out if your oscillator is made of a mass on a stiff spring, then the rate at which it'll oscillate is determined by the stiffness and the mass in this fashion. And that's a truism from now on. Like if you're looking for things to memorize or take to the bank, you could take that to the bank. So I'm gonna plug into that and I'm gonna finish the problem just so we have some closure. But that is definitely an important result that we need to know now. And it is, again, it's another step in connecting between the mathematics of a circle to the physics of a cycle, to the very specific physics of specific cycles in mass spring oscillators. Okay, so I'm just going to finish the problem. So I'm going to plug in. So here, so step 4, PAW, particular application work here. K equals, I don't even remember now. Okay, M was given, yeah. Ooh, why did we do? Oh, that was bad. I think it was, they probably were trying to do numbers that, oh, well, it's not a very nice number, is it? I think they were, I bet that wasn't the intention, but okay. Um, so this is the answer. Okay. Okay, so that's the answer to that. I'm just looking at it. That's just the answer, 28.3 radians per second, right? That yeah, let me just finish the problem. There's okay. So now we're doing part B. And again, C diagram above. Okay, so now we're asking for the period. So now, oh, I think, oh, I'm sorry. Oh, no, I skipped a question. I'm sorry, I skipped a question, didn't I? No, I don't know why the questions are being asked in this order, but so it's asking for the amplitude now. Now, the amplitude, if you just look at the picture, and you just look at the facts, the initial position of this oscillator is 3 centimeters from equilibrium. So that is the max. Let me put it this way. Or I guess this is just to define vocabulary. So just to be clear, I think everybody knows this, but from now on, like amplitude means maximum displacement from equilibrium. Amplitude means maximum displacement from equilibrium from now on. And it's it's usually abbreviated with the letter A. X naught means initial displacement from equilibrium. Right? So A means maximum. A, amplitude, refers to the maximum in terms of triple equal signs here. A refers to the maximum displacement from equilibrium. X naught, whenever we use it, refers to initial, like starting displacement from equilibrium. So those are two different meanings, but the whole thing is oscillators conserve energy. Thus, double equal sign for the kind of oscillators we're talking about, harmonic oscillators, the initial displacement from equilibrium does turn out to be the maximum displacement from equilibrium. They're one and the same, okay? Which I think you already intuitively know, but that's because of energy conservation. So which came from the first homework sheet. So we can use those terms interchangeably, A and X naught. Therefore, in this problem, just to be clear, step 4, PAW, here, X naught was given as 3 centimeters or 0.03 meters. So step 5, the answer here is that A equals 0.03 meters, or 3 centimeters. So that's the answer to that one. That but B, find the period for the, so B now, I'm moving on in the problems. Stop me if you don't want me to. B now asks for the period. Okay, I'm going to stop labeling all the steps now. It's asking for the period. So this is where I'm going to use the thing that somebody in the direct chat mentioned a second ago. Here, I'll just say, so I'm not writing the steps anymore. It seems to me that W equals 2 pi over T. Like now I have W. So W, now I have omega, the angular frequency. So now I can relate to cycling rate. So I can flip that around. If omega equals 2 pi over T, then necessarily T equals 2 pi over omega. Right? You just cross multiply and then divide. So if T equals 2 pi over omega, and omega we said equaled equal 28.3. So that's the answer to that one. I'm trying to just get this done. Okay. My goal is 5:20. I know we go till 5:45. I know you haven't really had a break. I'm aware of that. I think, well, I'd like to at least finish this I'd like to finish this problem. I'd like to tie this all back to waves. I'd like to either. Why don't we? Let me finish it if you don't mind. I want to finish this problem just so we have some closure. Then if I can, I'll try to either give you a quick break or we'll end a little bit early or something like that. I mean, I am aware that you've just been sitting here this whole time. But as long as we're doing all this, I think it'd be good if we had closure and we were able to wrap this up. So I'm going to finish. So I'm going to go to C now. Again, I mean, I'm just going to try to sort of bang out the answers for C. Again, it's like you're all in different places. It's always going to be too fast for someone and too slow for someone else. I really want you to, at least in direct track, stop me if I'm doing something too quickly, because somewhere in some of this, someone needs something. I mean, I know that from looking at the homework and everything, and some people haven't done it at all. I know that too. But I can't. But anyway, you get my point. So I'm just going to keep going, but stop me if I shouldn't, or speed me up if I should. So because now C, oh, this is an old copy. Oh, one thing I got to say. All right, so C, it says find precisely where the mass will be located at each one of these various times. Just note, this is a bad copy. This might have thrown some of you off. Note in this sheet that hopefully you're looking at right now, these T's are supposed to be lowercase. I don't know, and if that threw you off, I understand. These are supposed to be T. So in each one of these, it's asking. Now, you may not have even noticed that at all. I don't know, but each one of these questions is asking when the time when the independent variable time is either 0 seconds or 1 second or 5 seconds. Just note that, especially if you haven't done this yet, you may want to note this when you go back and look, or when you're studying, because yes, as you would have noticed, there's a problem very similar to this on the practice exam, which means there's a problem like this probably on the exam. So just please note these are in fact, okay, I'm going to do that thing again. I hate to be annoying, but can you just acknowledge somehow if you understand these are supposed to be lowercase t's? Thank you, Tiki. Thank you, Sadie. All right, that's good enough for me. Thank you. That's Mira and thank you. All right, awesome. Okay, but I do apologize, and honestly, we corrected that at some point over the years, and then I just Xeroxed the wrong sheet. I guess I'm sorry, but okay. So here we go. I'm going to quickly, and by the way, thank you for smiling as you thumbed up that, because if I would find it very hard to smile if I were any of you at this point. But okay. So what do we do? For each of these, like 1, 2, 3, it's asking it's asking for each given T, what is X, right? That's the question in each case, right? So all it's asking you to do in each case, it's asking you now to use the GDP that we've got going here. It's asking you in each case to recognize that X equals X naught, or A, whatever you want to say, times cosine of omega T. And we're supposed to recognize at this point that omega equals the square root of K over M in each context. So this is a plug and chug over and over and over again, but I'll do one and then we'll just, so in case one, when T equals 0, so we're saying what's X when X equals A, cosine of 0. Well, cosine of 0 is 1. So 1 times A is A. So just, okay, I will pause for a second. The answer to the first one is A. This circles us all, no pun intended. This brings us all the way back, or all of these answers, but particularly this first answer is going to bring us all the way back to the beginning of class today, when somebody, I'm looking, when somebody, I feel like it was, I want to make sure it wasn't in private chat. Yes, no, it was in private chat, actually. Okay, so I'm not going to say the name, but somebody in private chat all the way at the beginning of class today said something about Professor Moses showing you that when you open the unit circle, you get a full cycle. Yes. And this is where we really see that. Like, to really connect this all now, the whole point is once you get used to the fact that cosine of 0 is 1 and cosine, and once you get used to the fact that cosine fluctuates or oscillates between 1 and -1 and back to 1 again, the whole point of this expression, and the video was trying to say this too, the whole point of this X equals X naught, I'm calling it X naught, whatever. the whole point of saying that x equals x naught times cosine of blah, 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 or saying x equals a times cosine of blah, 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 blah. It's that we're taking the whole cosine concept, the whole cosine thing that on a circle goes back and forth between 1 and -1 and 1, 1, -1, 1, 1, -1, 1. And then we're multiplying that cosine idea by a or by x naught, whatever you want to call it. We're multiplying it by the actual amplitude of the actual mass on the spring, so that our mass on the spring is not just going from 1 to -1 back to 1. It's multiplied by wherever it actually started. It started at 0.03 meters here. So it's going back and forth between 1 times 0.03 to -1 times 0.03, right? Our amplitude term just scales up or multiplies out the entire cosine function. So I don't know if that helps or not, but yes, like going back and forth on a spring is just like the horizontal shadow of something that's going back and forth on a circle. But we've now stretched the circle to make it the size of whatever our amplitude is. I don't know if that helps or not, but yes. So at time equals 0, x equals its full maximum of 0.3. I'll just keep going. And when t equals, so when t equals 1 second, x equals 0.03 times cosine of what is it, point? Of 28.3 times 1, right? And here's where I guess this is worth practicing. Notice for all of these now, you can do this on your calculator now. Now we're doing physics. You can do it on your calculator, but your calculator has to be in radian mode. Sorry, so that's supposed to be a 1, right? So your calculator's in radian mode. So you do the cosine of 28.3 in radian mode, and you multiply that by 0.03, and you get a negative number, 0.02, well, approximately. You get, oh, I'm such an idiot. Wait, am I an idiot? No, I'm not an idiot, but okay. So you get like 0.03, which is interesting. Okay, then when t equals 5, you plug in for 5. I have a feeling we're going to get almost. Yeah, I see what's happening. Okay. The numbers were picked somewhat deliberately here, but I'm not going to dwell on it. I'm just going to keep going. So now, okay. Now the next couple of questions, I guess this is good. So those were just plug and chug into the cosine function, make sure you're in radian mode. But now it's asking you to be like logical, to really see that you understand, like basically what I was just yelling about. So when t equals t, when the time is 1 full cycle, where is the mass? Well, if it's 1 full cycle, it means it goes there and it comes back. So it's wherever it started. So for 1 full cycle, x would be 0.03. Like that's exactly where it started, right? And then when it asks in number 5, I'm going to leave this to you now. Okay. When I'm going to leave this to you. We're making tracks. When t equals t over 4, when lowercase t equals capital T over 4, i.e., when it's a quarter of a cycle, where is the mass? I'm asking you, what's the answer to this, to question 5? If I get 2 answers in the chat, I'll consider myself lucky and I'll move on. But what, so I'm asking the answer for question 5. So like the question is at t equals a fourth of the period. And you can, even whether you did the homework or not, if you look at it now, if you look at everything based on what we've been saying, we're asking, where is the mass at a quarter of a cycle into its motion, right? It's starting at 0.03 meters. It's starting at 0.03. If you do a full cycle of motion, it goes all the way to negative 0.03 and back to 0.03. That's a full cycle. But we're asking now, where is it if it does not a full cycle, not a half cycle, but a quarter cycle? Where is the mass? You know what, actually, because it's 5:30, if I get one person in the chat, I'll consider myself lucky and we'll move on. But I do want to get one person, because I do want to make, I mean, as long as we've hung in this long, let's hang in for the end. Where is the mass? And I'm telling you, you can figure this out just by looking at it now. You don't need a calculator. You don't, like, you just need to think about the concept. If a mass is going like this, back and forth and back and forth, if it starts here and it goes to equilibrium and all the way to the other side and then back to equilibrium and back to where it started, a quarter of a cycle into its motion, where is it? I could ask a slightly easier question if it helped. I shouldn't say easy, but where is the mass a half cycle? If it's going back and forth between 0.03 and negative 0.03 and back to 0.03 and back to negative 0.03 and 0.03. So it starts at 0.03. Where is it a half a cycle into its motion? Oh, sorry, Tiggy. Yes, I'm sorry. Oh, thank you. I'm sorry. I was getting sorry. I wasn't looking. Yes. She just saved the ship. Thank you, Tiggy. Yes. And she's answering the actual question, not the stepwise question. Yes, she is. Oh, did I write it already before you even, had I written it already the whole time? Like while I was yelling? Okay. Well, I guess, but she's right no matter what. At least she's paying attention. Thank you, Tiggy. Yes, the answer is 0. Like she was tweeting with her. It's 0 because but I want you. Okay, I know it's like really late. We got to wrap up. You need a break, you need to leave early because I didn't give you a break. I get all that. And we're just about done because we really actually have done a lot. But from here on in, if you ever picture a quarter of a cycle, picture the equilibrium. Like a full cycle means all the way there and all the way back. 2 pi radians means all the way there and all the way back. Therefore, pi radians, a half a cycle, means all the way there. And when I say there, I mean the other side, the negative amplitude. So therefore, a quarter cycle isn't all the way there. It's halfway there. It's to the equilibrium point for whatever it's worth. Or is that a question? Or you're good to, or no, okay, that's just your finger. Okay, so that's the answer to that. We're just about done. So then, and I'm just going to assume we've already answered the question in 6. Where is it when where is when t equals t over 2, where is x, what is x? And I basically just answered that question. Then x equals negative 0.03 meters. It's like, okay, a half a cycle is the other side. And finally, when t equals pi over 2 divided by the frequency, angular frequency, like pi over 2 is a quarter of a cycle, right? I mean, pi over 2 is a quarter of a cycle. So this is a way of saying what is the cosine of pi over 2? Cosine of pi over 2 is 0. It's just the same question asked again. This is just reinforcing. Question 7 is just asking the same thing as question 5, but in a different way. It's just reinforcing that a quarter, just note, if there's no other takeaway from this class, it's that pi over 2 radians equals a quarter of a cycle. Like that's what we sort of began the class with. That's what we're ending the class with. And then finally, to finish this whole sheet, I'm going to just do this last question. It's going to take me 2 words. and then we're done for the, and then we'll end like 7 minutes early, as in that would have been the break. Question 5 says, in this new experiment, the only thing we change is A. We leave everything constant, specifically K and M. We leave everything constant except for A. And it's asking now, what is the new period? And here is the point. Here's the big takeaway. The big takeaway of this is if the only thing we change is A, then none of our answers to T or omega or F are going to change. The thing I want to emphasize right now, if omega equals square root of K over M, which you learned in the lab, right? If omega equals K over M, the big implication of that, and it is a big implication, this means that angular frequency and therefore standard frequency and therefore period, all those things that are 3 different ways of measuring the same thing, all of those things are fully determined by what are known as parameters. They are fully determined by K and M, right? What do I mean by parameters? I'm just saying this and we're going to go. Parameters are material properties of system ingredients as opposed to ways of configuring the system. I'm saying this. This is my last bit. I'm saying this. The rate at which this thing cycles is 100% determined by the ingredients of the system, the stiffness of the spring and the heaviness of the mass. You put the heaviness of the mass on the table, you put that stiff spring on the table, anybody could walk in, see that mass, see that spring and go, oh, since I know omega equals square root of K over M, I know how fast that thing is going to go back and forth no matter what. They don't have to know how you configure the system. What I'm saying is omega is not a function of amplitude. The frequency, it does not, the rate at which this thing goes back and forth in time, frequency in time does not depend on configuration in space. It doesn't matter how big these swings are in space. They will, no matter what, take the same amount of time. That's a huge revelation. That fact that these swings are going to take the same amount of time, no matter whether they're going from all the way here to all the way there and back, or just like really small and quick, or really long and slow, they will take the same amount of time no matter what. That fact, which is the case, that fact is the meaning of the term harmonic. I know I said this in the video, I'm just emphasizing it now and we're done. When we call these, oscillation is any kind of back and forth cyclical motion. But when the oscillation has this property that the frequency in time is independent of the configuration in space, when the frequency in time is fully determined by what ingredients we put together in the system, then that type of oscillation is called harmonic. That's what this whole topic is about. You need harmonic oscillators in order to make the waves that you made in the lab last week and that we'll talk about in much more detail next Thursday. But you've been very patient and you didn't get a break, so let's leave 6 minutes. I guess I still owe you a couple of minutes in your life, but let's leave 6 minutes early now. I mean, I'll stay for questions if anybody has any. I'm here, but thank you for being so patient and active. And there's no new homework because we still have to catch up with other stuff. So have a great week, and I'll see you on Thursday. Thank you. And thank you for being, thank you for the waves. Thank you for the thumbs up. Thank you for being good human beings. And
Thank you, Professor.
thank you.
Thank you, Professor.
Thank you very much.
Thank you, Professor.
Thank you, guys.
Have a good night, Professor. Thank you.
Thank you for, yes, thank you too. Thank you for, yes. Okay, thank you. I'm turning off the recording if anybody has any questions.